Hey guys, this is Darshan Lokhande. I am a pre-final year BTech CSE student at IIIT Pune. Welcome to our channel Learn Competitive Programming with CodeChef. If you are interested in competitive programming and want to learn data structures and algorithms, this is the one-stop destination for you. We post weekly problem explanations and concept videos. So don't forget to subscribe to our channel by hitting that subscribe button and also the bell icon. The problem that we are going to discuss today is alien invasion. The problem appeared in August lunchtime challenge and has a difficulty level of easy. The prerequisites for this problem are binary search. The agenda for today is going to be as follows. First, we will walk through the problem statement and try to understand what the problem is trying to say. Then, we will see the quick explanation of the solution for this problem, followed by which we will see the detailed explanation wherein we will know that why binary search works in the first place. And at the end, we will see the pseudocode followed by the implementation of the same in C++. The problem statement goes as follows. Uh, there are n alien spaceships numbered 1 through n planning to invade Earth, and it is given that the ith spaceship will appear on the radar at time Ci. Also, it is given that each spaceship needs d time to reach Earth once it appears on the radar. Okay, so there are some number of spaceships who are going to appear at some particular time on the radar and then they will take d time to reach Earth. Cool. Now it's given that Chef owns a huge laser cannon which can destroy a spaceship in one shot. However, once the cannon is used, it needs some amount of cooldown time so that it can be used again. This cooldown time, however, is configurable. That is, it has to be set before the first shot and then it cannot be changed for the upcoming all shots. It is also given that if Chef sets a lower cooldown time, that would increase the energy consumed and vice versa. So also it's given that it is a long battle. So Chef wants to use as little energy as possible, meaning that he wants the cooldown time to be as maximum as possible. So we want to find the maximum cooldown time possible such that each of the spaceship is destroyed and the Earth is safe. So in particular, it is given here that to destroy a spaceship, it should be shot between the times Ci and Ci plus d, both inclusive. Coming to the input format, the input is pretty much standard. T test cases, each test case contains the two integers n and d followed by n space separated integers c1, c2, c3 up to cn, which denote the time at which the spaceship appears at the radar. Cool. Now output. Output is important. Please notice that for each test case, we have to output one real number, that is the maximum cooldown time we can set. Also, the relative error of the answer should not exceed 10 to the power minus 6. That is, your answer should contain at least 6 decimal digits with correct precision. So we have to take care of that while writing the solution and or more precisely while outputting the solution. The constraints are pretty much standard. There are 1000 test cases and n may go from 2 to 10 to the power 5. The CI can range from 1 to 10 to the power 9, but notice that sum of n over all test cases does not exceed 10 to the power 6. So this right here can also prove to be a major hint that we have to use binary search for this problem. At this point of time, I would like to mention that if you haven't yet tried the question, give it a try and then come back to the video and continue with the editorial. Great. So now that we have read the question, let's try to understand the task by seeing a small example. So the question says that we have Earth over here and over here, and also at some distance we have a radar on which the spaceships are going to appear at some time and then they are going to invade the Earth. Okay, so let's say the spaceships, we have three spaceships over here, and let's say one of them appears at time t is equals to 3, another appears at time t is equals to 9, and the third one appears at time t is equals to 12 on our radar. Okay, and once they appear on the radar, they take some constant amount of time to reach the Earth. So let's say that constant amount of time d is given as d is equals to 2. Okay, so they are obviously going to invade the Earth. But how are we going to save it? We are going to save with help of a cannon that we have on Earth, which we can use to fire and destroy the ship instantaneously. But wait, there's again a catch. Once the cannon fires a shot, it needs some time to cool down or reload. Okay, so that time, let's call that time as CD, cool down time. Okay, so this time is upon us to set. That is, once we have set the cooldown time before the first shot, we cannot change it thereafter. It remains constant throughout. Okay, and the window in which we can shoot the spaceship down is the one wherein the spaceship appears on the radar and reaches the Earth in time d. So this window time of time d is in which we can shoot down the spaceship. So without wasting time, let's try out some numbers. So let's say that we first of all take our cooldown time as 7. So what will happen? The first spaceship will appear on the radar at time t is equals to 3 and we can shoot it down at the same time. So we shoot at t is equals to 3. But now once we have shot at t is equals to 3, we cannot shoot until t is equals to 10. So we have to wait. Until then, the second spaceship will appear here on the radar at t is equals to 9 and it will take t until t is equals to 11 to reach the Earth. So we can fire our second shot at t is equals to 10 and shoot down the second spaceship. But now what will happen? Now we have to wait until t is equals to 17 for our cannon to reload. And until then, what will happen is that the third spaceship will reach the radar at t is equals to 12 and until t is equals to 14, it would have already reached the Earth. Hence, we cannot save Earth with a cooldown time as t is equals to 7, right? So now let's take another cooldown time. So for example, we take cooldown as 5. What will be the case with 5? The first spaceship will appear on the radar at t is equals to 3 and we shoot at the same time. Now we have to wait until t is equals to 8 for our cannon to reload. Then when at t is equals to 9 the second spaceship arrives, we can clearly shoot it down as we are already reloaded. Now we have to wait until t is equals to 14 for our cannon to reload. And until then the third spaceship would have arrived at the radar and when it will be reaching the Earth just at t is equals to 14, we can shoot it down at t is equals to 14 and save the Earth. So you just saw that how close we were to not saving the Earth. But luckily with cooldown time as 5, we could possibly save the Earth. Right. Now, if we take a smaller example for let's say cooldown time as 3, then what will happen? We can fire our first shot at t is equals to 3, wait until t is equals to 6 for reloading. Then at t is equals to 9, we can fire our second shot and kill the second spaceship. Then again we have to wait till t is equals to 12 for reloading. And then when the third spaceship arrives at the radar at t is equals to 12, we can shoot it down and save the Earth. So clearly we can see that some cooldown times are not able to save the Earth, whereas some cooldown times are able to save the Earth. And also in the ones that are able to save the Earth, some are able to save on a very edge case, that is on the very boundary, whereas some are easily able to save the Earth. So what is the question? The question is that we have to find a cooldown time which is higher enough so that we consume less energy as mentioned in the question, and at the same time we are also able to save the Earth. So before we start building up our solution, there are some observations which you can note. A minor observation can be that whatever be the arrival times of the spaceships, they always appear on the radar in increasing order only. meaning that whether it be given as 9, 3, 12 or 3, 12, 9, it will always appear on the radar in the same order. That is, first t is equals to 3, then t is equals to 9, then t is equals to 12. And also on from this we can also say that as all of them take same time to reach Earth, that is in our example d is equals to 2. So the first spaceship will reach at t is equals to 5. The second spaceship will reach Earth at time t is equals to 11, and the third spaceship will reach Earth at time t is equals to 14. So these both times are, as you can see, in increasing order. The other major thing that you can observe is that if we have x as our cooldown time, then there are only two possibilities. Either we can save Earth with x as our cooldown time, or we cannot save Earth with x as our cooldown time. Now, what does this two things mean? The fact that we cannot save Earth means that at least one spaceship has reached Earth, right? The fact that we cannot save Earth means that at least one spaceship has reached Earth and we weren't able to shoot it down. And we can save Earth means that we were able to shoot all the spaceships down and save the Earth. So this is a good case for us, and this is a bad case for us. We will later see that if given x as our cooldown time, then how can we reach at the conclusion that we will be able to save it or we won't be able to save it. This part will be handled in the later part of the video. So with this observation, it is safe to say that we can save Earth if our cooldown time is less than or equal to x in this case, and in this case, if our cooldown time is greater than or equal to x, then we cannot save Earth. Why? Because if I can save Earth with x as my cooldown time, if I lower the time, then I can definitely save Earth. But if I can't shoot a single uh, at least one ship with my cooldown time as x, then increasing the time won't help me. That is, I will not be able to save the Earth. So now I can state the question in other terms. What I mean to say is that we are going to have an ordered search space from 0 to some limit, wherein it is going to be a series of some yes answers followed by some no answers. Okay, what do I mean by yes and no? Yes means that I can save Earth with this as my cooldown time, with this as my cooldown time, and with no, I mean that I cannot save Earth. So there must be some boundary, right? Like the boundary, like just before which I can save Earth, and just after that I can't save Earth. So our target in the question is going to be finding this very point in our ordered search space. Okay, so this is going to be our answer. Our target should be to find a real number as close as possible to this answer. And note that this answer point can occur anywhere between our 0 and limit, right? So we don't know where it is going to occur. So let's say that we sample out some random points, like I look for the answer at this point and I get the response at as no. So using this response I am going to get as close to the answer. Also if I randomly sample a point around here, so I will definitely get the answer as yes. So using that answer I will go as close to my answer point as possible. So we just saw that our answer can lie between 0 and some limit. But to find the answer, we need some finite limit because we have to work with numbers, right? So to analyze it, let's go back to our example. So our beginning example was that one spaceship arrives on the radar at t is equals to 3, the other one at 9, and the third one at 12. And the time taken to reach Earth from the radar is 2. So let's say the last ship that is going to arrive is the third one, right? So the third ship will arrive on the radar at time t is equals to 12 and reach Earth at time t is equals to 14. So if I keep my cooldown time as, let's say, 14, it means that if I fire a shot at t is equals to 3, then the next shot that I will be able to fire will be at t is equals to 17. But to be precautious, if I, let's say, keep my upper limit as 15, then I will definitely not be able to shoot the third spaceship. Why? Because even if I fire my shot hypothetically at t is equals to 0, then also my reload will take place for 15 time units, and then at t is equals to 14, I will be at t is equals to 15, sorry, I will be available again to shoot. But until then, the ship would have already reached the earth. So for now, let's take 15 as our upper limit. Later in our discussion, we will generalize this upper limit for each and every test case so that we don't face a problem while writing the code. Okay. So now coming to the next point, we said that we would be using the set of yes no answers to get close to our actual answer. How will we actually doing that? So let's say that our answer lies somewhere around here. Okay, it can lie anywhere, right? And I randomly sample a point and get an answer as no. So I know that the values of cooldown time greater than this point are of no use. So I will reduce my search space to just this. Okay, so now my search space is just this. Then again, I randomly sample a point, let's say over here, and I get the answer as yes. So I know that I can save Earth with this as my cooldown time, but the value smaller than this will only lead to me consuming more energy. So I will ignore this segment and further reduce my search space to just this. So in a way, we will be taking random sample points and getting the feedbacks from that point as yes or no. And then based on that, we will be eliminating either segment about the point and getting as close as possible to our answer. So I have been saying that I will point out some random points and get feedback from there to get close to the answer. But a question might pop in your head that why random, right? See, it's correct. Why random? Let's go order, right? So what we'll do is in our search space, we will first random instead of going random, first we will check the answer or the feedback for the middle point, right? And based on that, we will eliminate either segment about this point. Okay, so either segment about this point will be eliminated. Let's say we get a feedback as yes. So in that case, the first segment will be eliminated and we will be left with half of our original search space. Again, repeatedly, we will choose the middle point of the current search space and get the feedback. Let's say we get the feedback as no. So we will exclude the second segment, right? And the search space will be further reduced to half of the original search space. So in this way, at each step, we will be reducing our search space by half and getting close and close to the answer. So now the only question that you get is how to get the yes no feedback, right? So let's assume that our cannon, okay, our cannon has a clock on it, okay, a clock that at beginning reads t is equals to 0, okay. What it means? It means that at t is equals to 0, the cannon is waiting for someone to arrive and so that it can shoot it. Right. Now, as we discussed, the ships will arrive at in increasing order, right? That is first t is equals to 3, then t is equals to 9, then t is equals to 12. Okay, and let's say we are doing an example for cooldown time of 4. Okay, so at t is equals to 0, the cannon is waiting for the spaceship to arrive. So as soon as the spaceship arrives at t is equals to 3, the cannon shoots and the next time at which it will be free will be t is equals to 7, right? So once it is free at t is equals to 7, the next spaceship will arrive at t is equals to 9 and then he shoots at 9 and now the clock will read t is equals to 13. Why? Because he shot at 9 and now there is a cooldown time of 4. So the next time at which it will be free is t is equals to 13. So now the third spaceship will arrive at t is equals to 12 and it will start entering the earth. It will start entering earth, and in between at t is equals to 13, when the cannon is free, it will shoot it down at t is equals to 13. So what we saw is that there are only three possibilities for the time, right? The three possibilities for the time are either your time can be less than the appear time of the spaceship on the radar, or your time can be less than or equal to the appear time plus the time to reach earth. Okay, so either your time can be less than your appear time or your time can be in the window, right? uh, so in both the cases you can see that we are successfully able to shoot the ships. But if your time that your cannon reads is greater than this appear time plus d, it means that the ship has already reached earth, so you cannot save earth. So this is a bad case and all these are good cases. So for all the ships, if these two conditions are satisfied, then we can say that we can save earth. But if at any point if this condition occurs, then we cannot save earth. So now the solution is almost ready. The solution is as follows. We will have a lower limit for our search space. Let's define it as low is equals to 0, and an upper limit high, which is going to be 2 into 10 to the power 9. How did we arrive at this number? Remember that the last spaceship can reach radar at time 10 to the power 9 according to the constraints mentioned in the question, and also it can take maximum time 10 to the power 9 to reach earth. Okay, so combining these two, the maximum possible cooldown time that we can have is 2 into 10 to the power 9, but to be safe we will keep it as 10 to the power 10. So in this range 0 to 10 to the power 10, we are going to apply the solution that we just discussed. That is, we will find out the midpoint, find out the answer for the midpoint, that is yes or no, and based on that reduce our search space by half, and we will keep on doing this until we are very close to the answer. But what do you mean by very close to the answer? That is, till when do you have to apply this method? So we have to apply or reduce our search space by half until and unless our search space itself is greater than 10 to the power minus 6, which is the relative error mentioned in the question. So until and unless our search space is bigger than this number, we will keep on applying and reduce our search space. And once the search space is less than 10 to the power minus 6, then whatever will be the value of low at that point will be our answer. Why? Because as you can see at all the steps, the low or the new low for the corresponding next search space, low is always able to save earth. Okay, that is, if we have cooldown time as low, we are always able to save earth. Finally, we have our solution ready. So now I would like to mention that the approach that we just saw to find the answer is known as binary search on answer, right? So the concept is nothing but binary search on answer. Why it is called binary search on answer? Because we saw that we had a huge range of real numbers in which we had to find our answer, and it was somewhere in between. It can be anywhere, right? The answer can be anywhere, and using binary search techniques, that is taking a midpoint and based on the feedback reducing the search space into half, we got close to the answer. So this concept is known as binary search on answer. It is slightly different than the classical binary search that you might already know, which involves searching a number in a sorted array. So now that we have seen the solution and its detailed explanation, let's use our knowledge to build the pseudocode and then code it in C++. So the pseudocode goes as follows. So initially we will be beginning with low equals to 0 0.0 and high equals to 10 to the power 10. And on this search space, we will be applying binary search on answer. So as discussed in the solution, we will be doing this while the difference between high and low is greater than 10 to the power minus 6, which is the defined precision in the question. So for each step, we will find the mid and check if it works out. So if the mid works out to be a safe reloading time, then we update our low, or else we update our high. So how to check if it is a good reload time? As discussed in the detailed solution, we first of all we have to sort the arrival times, so that we can do before starting our binary search only. So we can sort all arrival times and then apply this work function. So what we will do is we will set our current time to be 0 0.0, and then for each spaceship arriving we will check that okay, if I can shoot it beforehand, then it's good. If I can shoot it in the given window of the D time, then also it is good. Else it's not a good reload time or a good cooldown time, then I return false. So in this manner, this loop will go on, and at the end, I will output my answer as low. So now that we have seen the pseudocode, let's get to the implementation part. So I will be implementing the code in C++. So the code begins with taking input for t test cases. So I will just take t and iterate and loop while t minus minus. For each test case, I have to take two numbers n and d denoting the number of spaceships and the window in which the spaceship can enter from radar to Earth. So I'll just take the input n and d. Note that I will be using global variables as I require them in other functions as well. So I'll just declare n and d here globally. Next, I have to take input for the arrival times of the n spaceships. So for that, I will create a global vector named C, and I will initialize it with size n. So C is equals to vector int of size n. And now I have to take input for the arrival times of each of these spaceships. So I'll do that by making a for loop. Great. So now that we have taken the input for each of these spaceships, we need to sort the arrival times. So we'll do that by using the inbuilt sort function. So sort c.begin, c.end. So we have now sorted the arrival times of the spaceships. Now note that we have to now start iterating through our binary search. So for that we require two variables, low and high. So I will be declaring them of the type long double because we require a precision of 10 to the power minus 6. So I'll just declare two variables, low and high, with values 1e10, that is 10 to the power 10, and low as 0 0.0. So these variables are my initial search space in which I am going to find my answer. And I'll also be requiring a variable known as mid. So I'll just declare it here only. Great. Now I'll start applying my binary search. So it goes something like this. So as discussed, while high minus low is greater than 1, 2, 3, 4, 5, or let's say, yeah. So while my high minus low is greater than 10 to the power minus 6, I'm good to apply my binary search. So while this is true, uh, my mid is equals to low plus high divided by 2. And now I have to see that if this mid is a safe cooldown time, then I will update my low or else I will update my high. So if work of mid, that is if this is true, then low is equals to mid, else high is equals to mid. Okay, and after this all thing is done, I have to just output my low over here. So we'll do that afterwards. So first I need to define this function work. So to define this function, I'll just write here, it will be return either true or false. So the return type will be bool. So bool work, and the only parameter will be mid, right, of the type long double. So long double mid. Now I have to initialize my starting time as 0. So I'll just initialize time as 0 0.0, and then for each spaceship I have to check whether I am able to shoot it. So for int I equals to 0, I less than n, I plus plus, if my current time is less than the ship's arrival time, I can clearly shoot it. So I will update my time as ci plus mid. Okay. Else if my time is less than or equals to ci plus d, that is my time lies in the window in which it reaches from the radar to earth, then also I will be able to shoot it, but then my time will be updated as follows: time plus equals to mid. Else I will not be able to shoot it, so I will return false over here. And if this whole for loop works out and I shoot down all possible ships, so I will just return true over here. So okay, we are done with the work function. So now that the work function is complete, I think we are free to output our answer. So we'll just output our answer. So cout low. But wait, it is mentioned in the question that the relative error should be less than 10 to the power minus 6. It means that we have to give some precision. So we have to write fixed set precision. I will set it as 7 to be safe. So I'll just output low over here and then give a new line. But there is also another thing that we are forgetting. It At the beginning of the code, we told that we will be using these global variables. And as this is a global array, so we need to clear it after we are done using it. So while I take input for each test case, I will make sure that I clear my previous vector. So now let's see if this code works out by submitting it on CodeChef ID. And let's hope for a quick AC. Great, so our solution works. Now, regarding the complexity of this problem of our solution, we can clearly see that for each test case, we are applying a binary search, and then for each possible candidate, we are checking if it is a good reload time by iterating through the loop once. So the complexity will be n log n.